Hi everyone, my name is Ximing Yu, software engineer at Facebook. Today I'm going to talk about Bladerunner, the solution we built at Facebook, which helps keep a live view of social graph data on hundreds of millions of end users' devices. Here's the agenda of the talk. We'll start from the problem statement to explain why keeping live view of data on user devices is a challenging problem at Facebook scale. Then we'll go through high-level data flow and then dig into components involved with design choices we made. Lastly, we'll talk about our experience operating Bladerunner in production over the past 5 years with some data. Facebook offers different services to end users, such as newsfeed, video, and groups. Those services are powered by a large social graph with billions of nodes and edges. The social graph data is stored in tau, which distributes data to multiple geographical regions and provides low latency access to social graph data via caching. While tau provides access to social graph data via simple point and range query APIs, it is pretty challenging to keep the view of data live and up to date on user devices because of the following reasons. Firstly, the social graph is constantly mutating, and some parts can be mutated at a high velocity. Some contents are time sensitive and will become less engaging if delivered to a user with high latency. Secondly, users of Facebook services also change their focus of interest very frequently. Data to load for a client cannot be predicted ahead of time, and thus we can simply maintain a single data stream and sync it to the device. Lastly, users access Facebook services via mobile devices or web browsers. Those client devices have limited processing power and storage capacity. To provide a smooth and responsive user experience, we have to limit how much data to process on client devices. To solve this problem, one solution that existed for years is polling. When user opens a surface on the client, it issues a query to fetch data from server and then periodically polls latest data from server for updates. This is easy to implement, but we have found this solution to be problematic. When looking at the parts of social graph being queried by end user devices, most parts are pretty static. Only a small proportion of the social graph is being mutated at high velocity. Therefore, polling will lead to a lot of wasted queries, which do not return any new data. This is a waste of network bandwidth and client battery. Polling also leads to high overhead on server side because polling might incur ranged queries and intersection queries that are costly. Lastly, there is an inherent latency because of the polling interval. New data won't reach client until the next poll happens. Therefore, we need a more efficient and more real-time solution, which is Bladerunner. Now, let's look into the high-level data flow. Client devices continue to issue queries and mutations to tau using request-response style interactions. On top of the existing interactions, we start to publish updates to a service called Pylon after committing mutation to tau. Pylon then fan out updates to BRAS instances, which maintain long-running streams over persistent connections to client devices. For each connected client device, BRAS push real-time updates to the client. Here are some more details on read path and write path. On read path, the client first issue a GraphQL query to fetch data needed to render the UI. After obtaining data from GraphQL query, and usually after UI rendering is complete, GraphQL subscriptions are issued to register their interest in receiving real-time updates. Both the initial query and follow-up subscriptions are using GraphQL so that it is easy for clients to reuse common data models. For each GraphQL subscription, a long-running stream will be established from client and they will land on BRAS servers. Subscription requests will be resolved by web application server into a concrete topic, and BRAS registers subscription to the topic by calling Pylon. On write path, when client issues a mutation to the social graph, the GraphQL mutation will hit web application server and then commit the mutation to tau. After tau acknowledges the mutation, an observer is executed in the web application server to emit an event. To ensure the tau mutation can be observed by all subscribing clients with read after write consistency across all regions, the observer will also capture a flight tracker ticket. The event and ticket together are wrapped into a publish request to a topic, and it invokes a published pylon. Pylon fan out events to all subscribed BRAS hosts, and then inside BRAS hosts, there is an in-process fan out to all stream processors. The application-specific processor makes delivery decisions on a per-stream basis. If the decision is to deliver the event to client device, BRAS will make a call to web application server to perform another round of privacy check and load data from tau, conditioned on flight tracker tickets. And lastly, the GraphQL payload will be delivered to clients. Now, let's dive into concrete components involved and discuss some design choices we made and their rationale. Pylon is a simple in-data center pub/sub system that fan out messages to RAS hosts. Pylon maintains a distributed in-memory key-value data store for storing mapping from topic to subscribed RAS hosts. Each published message is delivered to all subscribed RAS hosts in a best effort fashion. There is no ordering for publishes to a topic because fan-out is performed statelessly. RAS instances are responsible for application-specific stream processing. Each RAS runs in its own isolated environment, a JavaScript V8 VM, and can process streams from the same product use case. Each RAS host runs multiple RAS VMs. Number of RAS VMs to run for a product use case can be scaled automatically based on load. The fleet of RAS hosts provide us serverless compute environments that is specialized for long-running streams. Burst is an application layer protocol developed to support long-running streams between client devices and RASes. Each stream is routed independently across multiple hops. Burst provides a uniform networking API to Bladerunner application to allow different network protocols between edge and client stacks. Burst also makes it easy to adopt new network protocols like HTTP3 without changing application code. Now, let's dive even deeper into failure handling. A stream can span across multiple hops, and each hop can fail independently. Burst guarantees that upstream failures are reliably signaled to downstream clients. Each hop can either automatically retry or delegate to application logic in client devices. Applications built on top of RAS and Burst have the flexibility to choose different levels of delivery guarantees. Today, most applications leverage best effort delivery because of Pylon, which only fan out to client devices with good end-to-end connectivity. If we replace Pylon with a distributed logging system that assigns sequence IDs to each event, we can provide guaranteed data delivery. Now let's dig into a concrete product use case. Real-time delivery of comments on a live video has been the product use case that kept stretching our infra and thus influenced the design of Bladerunner. An unthrottled stream of comments can easily overwhelm human beings and make the product unusable. It is also very hard to predict ahead of time if there will be a video that becomes viral and thus drive tons of interactions globally. Our solution involved ranking each comment before publishing to Pylon, and then inside RAS, we maintain a buffer of comment IDs and scores for each subscriber. New comment events are pushed into this buffer in real time. Periodically, RAS would flush the highest ranked comments to the clients, and comments older than 10 seconds are discarded. Throttling can kick in before publishing to Pylon by filtering out low-quality comments for videos that are extremely hot. One thing to note is that Bladerunner incurs only point query for individual comment objects, which is much cheaper than range query and followed by multi-shard point queries incurred by polling. Now, onto our production experience. For the live video comment product use case specifically, we saw both reduced latency in data delivery and huge efficiency wins after switching from polling to Bladerunner. For the use case alone, CPU load on web application server and number of tau queries decreased by a factor of 10. Globally, there is a 5% reduction of tau IO ops at peak, and global CPU load on web application server also reduced by 2.5% at peak. Bladerunner is now serving 3 billion active streams at peak, and we have seen Bladerunner making 4 billion delivery decisions per minute at peak. Here are some of our other learnings. Firstly, capturing all possible mutations to data stores that might change the result of a query execution is both difficult and unnecessary. Therefore, we require product developers to explicitly specify liveness requirements for their product surfaces. Secondly, Bladerunner requires product developers to rethink how ranking works for their products. When performing polling, it is okay to load a batch of items and rank them together. When using Bladerunner, individual items are pushed to clients, and the team would probably want to weigh between latest items versus most engaging items in their product experience. Thank you for listening. For more details, please see our paper on Bladerunner, and feel free to reach out to me if there is any question.